loss, the tragedy that we have lived in Brazil, like in some other countries. We have lost more than 600,000 people in the COVID pandemic. So we have to think of all these losses. Okay, now our subject is the Skyrmions. I will describe some types of Skyrmions. I will relate mention the relationship that links Skyrmions to topology. I will discuss some properties of Skyrmions and some applications of this novelty. The Skyrmions have had a very large impact when they were first discovered, the magnetic Skyrmions, I mean. And in many publications, it was seen that these objects had a very important possibilities of applications and new physical effects relating Skyrmions. They have interesting physical properties, and they were inaugurated by this paper written by Tom Skirb in 1962. This was a paper published in Nuclear Physics Journal, and it deals with the theory of nuclear physics. And although devoted to problems in nuclear physics, it raised many questions and formalism that was relevant to solid-state physics, especially to magnetism. Therefore, particles that had some properties related to those of Skyrm's theory were given the name Skyrmion. There are two major groups of Skyrmions shown here. On the left, these are the Bloch type of Skyrmion. It's a structure of magnetic moments tangential to circles, as shown in figure A. A second type of Skyrmions, very common, is the nail Skyrmion, where the moments are organized in radial planes, as shown in figure B. On the right-hand side, we also show how the moments, the magnetic moments, vary along the diameter. In the case of the Bloch-type Skyrmions, the diameter, the plane of the diameter, the moments are not contained in the plane of the diameter. They turn in and out of the plane. And in the nail type of Skyrmion, the moments are contained in the plane of the diameter. They turn, but inside the plane of the diameter. There are other structures related to these two-dimensional ones that I have shown. These are called, on the left, Hopfions, or in the center, these complex Skyrmion bundles, and also other related structure, the Skyrmion braid, shown on the right. These are recent publications that have shown these possibilities. The Skyrmions were predicted, the magnetic Skyrmions were predicted in the end of the 1980s by Bogdanov and Jablonski, and they were observed, experimented for the first time 20 years later in 2009, that is some 10 years ago. The illustration here shows that the Skyrmions can appear in lattices, as shown on the right. The topological properties of the Skyrmions that I would like to discuss, they are more easily introduced if one discusses the corresponding properties in domain walls. The stability of the schema is related to what's called the topology-related protection. And we are going to consider the meaning of this by using the physics of domain walls. I here show two domain walls on the left, two domains. One domain pointing toward the right, and on the right, one domain pointing towards the left, and an intermediate region, which is called a domain wall, which is shown in green here. The topological charge, which is a quantity that characterizes the different types of skyrmions, is to introduce it. I need to consider the quantity called the winding number or vorticity. As shown on the left here, we have two circles with the arrows indicating perhaps magnetic moments. On the first case, the arrows, as we turn around the circle, the angle that they turn is 0, and this corresponds to a winding number of 0. The second case is more complex, but again, the total angle rotation of the arrows is again 0, so this is also winding number 0. And in these two more or less obvious cases, the arrows turn 2 pi, therefore these are the winding number here is 1. The winding number is the angle that the moments turn divided by 2 pi. And from that number, we define the topological charge Q, which is a generalization of the winding number in the sense that it includes the out-of-plane effect. So Q is the product of W and P, where P is the polarity. It can be +1 or -1 in the skyrmions that point up or down. Yes. So then let us consider the one linear domain wall, as shown here on the top. I show here magnetic moments pointing up and one moment pointing down. This is called local soliton, local singularity here in this case. And in the second case, I have moments pointing upwards and moments pointing downwards. This is a non-local soliton. In this local case, if I turn one single moment, I destroy the soliton. Whereas here, to destroy this soliton, I have to move all these domains, all these arrows, that is, all these moments away. I cannot locally destroy this. So this is called the non-local soliton. Okay. Showing now, I have here 3 domains: domain 1, domain 2, domain 3. And the domain walls, which are these intermediate regions here, where the moments, as shown on the left, they turn clockwise. And there is one central domain, and the domain wall between this domain 2 and domain 3, again, the moments turn, but now they turn the opposite way. So if we add this deformation that turns clockwise and the deformation that turns counterclockwise, we had a 0. So this is a total winding number of 0. Whereas here, the same case, we have 3 domains, but the walls the second ball and the first ball, they both turn clockwise. So I cannot add these two in a way that I will show. And this is a winding number larger than the zero, not zero. This is illustrated very clearly in this case. Here I have our problems start here. I have an animation here that will not be visible because I'm in the way the mode I'm using to show the slide. Here I have three domains, and the moments turning counterclockwise here and clockwise here. And this is the effect. This is a micromagnetic simulation. This system of three domains under an applied field. After some time, the situation is like this, and like that. So this, after some time, the central domain is practically erased. It does not exist, and the situation is almost a single domain with no domain walls. I cannot show here what happens next. It's the same micromagnetic simulation now with the walls turning differently in the second case here, and therefore, if we have a chance of seeing this image, we would see that now the winding number is non-zero, and therefore, in the simulation with the same field, we do not see the disappearance of the central domain. You have to take my word. Okay, the macromagnetic simulation, which I have mentioned, is a way of demonstrating properties of nano or mesomagnetic objects. Usually, a classical description is given, and a semi-classical description is given, and the object of study is divided into cells, and each cell has the properties, the interactions that are taken into account in these simulations. They include basically the exchange interaction responsible for the magnetic order, the anisotropy interaction, and an interaction that's not normally discussed. This is a type of exchange, the Jablonski-Moria exchange. From the form of the interaction, we see that whereas the exchange interaction is minimized when the magnetic moments are parallel, here the magnetic moments in the energy minimum are non-parallel. They are perpendicular or non-parallel each other. Okay, these are two ways of representing the schemers. The one way of showing all the moments, the magnetic moments, as I had shown before, and then another way of showing this is to use a color code. The blue is meaning moments upwards, red moments downwards, and white moments in the plane of the paper. And so this block case, the nail case, can be represented in several ways. The Jablonski-Moria interaction, it is present in non-central symmetric crystals, i.e. crystals that lack an inversion center, and also in the surface where there is a discontinuity. Recently, it was shown that when there is geometric frustration, schemers may also be produced. Okay, now going back to the representation of magnetic moments. This is how the magnetic moments vary along a diameter, as I had mentioned. And these skyrmions are known as pi skyrmions because from the border to the center of the object, it turns pi radians. The same is observed here. They are both pi skyrmions. There are other types of skyrmions that, as illustrated here. These are again the pi skyrmions. Here I have a 2 pi skyrmion. The moments from the border to the center, they turn 2 pi. And other more complex skyrmions, for example, here with the 3 pi and here a 4 pi skyrmion. They have topological properties that are different, and as I will illustrate later. Other objects related to the skyrmions are the anti-skyrmions that have this geometry here, and illustrated in 2 different ways here. And one can obtain the different types of skyrmions by varying these parameters that have shown as relevant, which are the magnetic anisotropy and Charles-Moria interaction. We have examined when we want to illustrate a phase diagram where this is more visible. This axis here is the magnetic anisotropy. This axis here is the value of the Jaroszewski-Moria interaction. And if one follows this green arrow here, we start with the region where, for this value of the anisotropy, and this range of values of the Jaroszewski-Moria interaction, we have all these are single domain. Here we begin to find skyrmions. This is a skyrmion, simple skyrmion. Then we continue increasing the interaction D. We run into the green, which contains the 2 pi skyrmions. And if you continue, we find 3 pi skyrmions, 4 pi skyrmions, etc. So this is a phase diagram illustrating how these interactions are relevant and how they contribute to a given arrangement of moments, characterizing types of skyrmions. This is, we have motion here, which does not appear. This illustrates one of the very important properties of the skyrmions. They are moved by electric current, and they can be displaced, and which is very relevant for applications. On the left here, we have 2 examples where the top value has 1 megampere per square centimeter of current density, and the one here is 5 megampere per square centimeter. This corresponds to a current not very high because these are nanomagnetic objects with a thickness in the range of nanometers. So this is not a very large current. And these currents move the skyrmions to the right. Here is an example of an obstacle on the way of the skyrmion, and the simulation shows that on the first case, the skyrmion is blocked by this notch, and on the second case, with a somewhat higher current density, it avoids the obstacle. which is a very interesting property, of course. This is one of the physical effects that have been observed with the skyrmion. With skyrmions, this effect is that skyrmions, they move as shown in the previous slide, that they move with the current applied. Now here I'm drawing your attention to the fact that they do not propagate in straight line. They move away of the axis, and this has been called the skyrmion Hall effect. Unfortunately, this animation shows the text of this article, which will not appear now. The animation makes a parallel between the skyrmion Hall effect and the Magnus effect. In fact, this article here starts by mentioning that Brazilian footballers made a goal by inducing the turning motion of a football in such a way that the ball propagated in a non-straight way, and this is happening in the World Cup some years ago. And this is skyrmion Hall effect is analogous to the Magnus effect of mechanics, whereby a turning sphere propagating for example, inside a fluid or in air, it will deviate from a straight trajectory. And this skyrmion Hall effect is analogous to this effect. Here is again the same illustration, and different systems show deviations. This is a lump of skyrmions with skyrmion number very high, 46 or 18. Here I show that this skyrmion propagated along this line rather than going along the axis. A skyrmion with zero, Q equals 0, it propagates along the center of the magnetic strip where it's generated. The Q number, it varies. The simplest skyrmion has Q equals 1, plus or minus 1, as I have illustrated. This is a pi skyrmion. A 2 pi skyrmion shows compensation, and therefore Q is 0. This is the trajectory shown here. And Q plus or minus 1, this would involve deviation from a horizontal path. The skyrmion Hall effect is illustrated here. The whole angle is put here in the graph against topological charge. Topological charge 0, the angle is 0, no deviation. This is an interesting aspect of the skyrmions. If one desires to have propagation along very large distances, with the use of a skyrmion with Q equals 0 is more convenient because it will not deviate from the axis. Okay, another effect that is related to skyrmions is the topological Hall effect. The skyrmion Hall effect is this one described here by represented by this deviation, and the topological Hall effect arises from the interaction of the conduction electrons and the Skyrmion structure here. The, the complex structure of the Skyrmion interacts with the electrons, and the electrons are deviated. This is a type of Hall effect, which is called the topological Hall effect. So these are two effects that were observed with the Skyrmion. This is illustrated here with the field E and current moving from the left first. In this direction, the current is moving in this direction, and this there is the Hall effect occurs like this, and the electric field, the electrons with spin up and with spin down, they see different magnetic fields, and they are deviated by the Skyrmion, which is in fact by the topological charge of the Skyrmion in a way that is shown illustrated here. Field for one type of electron and field for other type of electron. When the Skyrmions began to be suggested in different applications, one of them was very visible, one of the most important applications, which is the application of Skyrmions in racetrack memory. Racetrack memories were originally proposed in IBM, memory devices using domain wall motion, and when the Skyrmions began the studies, it appeared that the Skyrmions could be used in the same way as domain walls, as I will illustrate here. This is how the proposal of the domain wall racetrack memory looks like. The proponent of this model was Stuart Parkin, and it shows here that this is a magnetic strip, and blue and red mean magnetizations in one way or the other way, and a current flowing through this racetrack moves the domains, and therefore they can be stored and analyzed. Here at the bottom, the domain walls are written in red, different devices in the bottom here. These are the best known domain wall racetrack domain wall memory. From this beginning of the discussions on the applications of Skyrmions, in the literature there appeared racetracks that have, instead of domain walls, they have Skyrmions. In the case of the domain walls, the bit 0 and 1 bit were represented by magnetization one way or the other. In the case of Skyrmion, bit 1 means the presence of one Skyrmion, and bit 0 means the absence of one Skyrmion. This is how the development of magnetic racetrack memories was started to join the development of the discussion of applications of Skyrmions. On the left here we see current. This is a graph of current density versus velocity, and we see it's hard to see here. There are two lines shown together here. One for domain walls and one for skyrmions. They coincide almost perfectly here, which means that increasing the driving current, the velocity of domain walls and skyrmions increases almost the same way. But at the beginning of this graph, it shows that for small currents, the behavior is very different. The behavior for domain walls is shown here. The domain wall does not move until a certain value, the depending value of the applied voltage density here. Whereas the skyrmions, they start almost with practically zero domain wall. Zero current density, they already start moving. And this is also illustrated here. An oscillating voltage will, in the case of domain walls, it will move the walls only when this value is reached, whereas the skyrmion will be started to move at this point here. Okay. These are shapes of the device proposed for memories, racetrack memories, with this linear geometry here. Domain walls, blue and red, are different domains pointing one, different magnetization, one pointing to the right or to the left, for example. And here, as I said, the bits represented by the presence or absence of skyrmions. These are the proposals they use already, what the ideas that were in the literature for the use of domain walls. This is an interesting effect here, where by applying a current, this is a very narrow part of a circuit in a larger part of, for example, strip, magnetic strip. Here, with the current from right to left, we have the motion of these domain walls. It moves. It is displayed as a domain wall. When it reaches this wider range, it turns into a skyrmion. So it moves in this part as a domain wall, as it has two domain walls, and it becomes a skyrmion here. The same motion is reversed by reversing the sign of the current, and we have here the same thing. It starts as skyrmion as it becomes two domain walls. So this is very convenient because an application and spintronic application may use the certain advantage of dealing with domain walls in one part of a circuit and the advantage given by the skyrmions in another part of the circuit. This is another device that's been proposed. Skyrmions come here and the circuit pushes them one way or the other way if they represent zeros or one. Therefore, this here, that's the way where the zeros go, and the ones go on the other side of the junction. So, reading the number of skyrmions present one side or the other side, one can read the information codified as zeros or one. The advantage of the skyrmions when compared to the domain walls, the size comparable, tens of nanometers, the speed more or less comparable, hundreds of the order of 100 meters per second. But in this comparison here, is very important the advantage of the skyrmion in terms of critical current. Critical current that starts the motion of the skyrmion. The skyrmion needs 10 to the 5 smaller critical currents to be moved. as compared to domain walls. This is also another comparison of the properties of domain walls and skyrmions. And in most cases, I put a green arrow, emphasizing the properties where the skyrmions are superior to the domain walls. The only obviously negative property of the skyrmions is reading the skyrmion. It's not very easy to make to read the presence of the skyrmions. These are variations. Racetrack. You have in the racetrack normally you have to empty the racetrack completely if you want to modify one single bit. One way of avoiding that is having connection between the bits. So the bits are moved until they reach this bridge here, and then the one single bit is modified. This is instruments, devices that can use skyrmions. Another aspect, interesting aspect, is this racetrack where one has skyrmions coming. It's a logic gate. When one has skyrmions coming from both sides, they merge here and produce one single skyrmion there. So one skyrmion and one skyrmion here, there is one output. So this is an OR gate that uses the fact that they merge using the flexibility of the skyrmions in this respect. The skyrmions, they also behave differently under different temperatures. Here we show the velocity of the skyrmions versus current density, and measured for different temperatures. And you see that increasing the temperature increases the velocity. And also in this case, this illustration here, that it's a simulation where the temperature difference between these two ends of a ribbon may induce the skyrmion to move. This is a very interesting possibility. This is the continuation of the same paper, showing that for different temperature gradients, the position varies more rapidly with the time. Therefore, a temperature gradient can be used to move skyrmions. This is a possibility that it's very interesting. This is also another study using motion of skyrmions with temperature. It's interesting because in the previous one, the skyrmion was moved from the hot part to the cold part. In this case, these were metallic samples in the previous case. Here, it's the case of an insulator where the skyrmion moves towards the hot part because the spin waves move the other way, and this pushes the skyrmion back. Therefore, magnum current makes the skyrmion move in the direction towards the hot part. This is illustrated here as well. Okay. This mentioning again this 2π skyrmions, also called skyrmioniums. They have no skyrmion Hall effect, as I said. They do not deviate laterally, as I have mentioned. Another fact is that the skyrmionium or 2π skyrmions are in red here, and the Skyrmions are in blue here, showing also that they move with higher velocity for the same value of current density. Interestingly, once one keeps increasing the current density, eventually destroys the skyrmionium. It begins to deform, like as shown here, and then they disappear. This is an advantage in some ways because it's a mechanism of erasing the skyrmioniums. Okay, the lay skyrmions have been used to design logic gates, circuits with this strange shape here have been designed. This is an AND gate. Skyrmion here. One skyrmion and 0 give no output. 0 and 0 give no output, and so on. So this is an AND gate. All the other gates have been prepared. It's a pity that I cannot show. I had animation here as well, showing how the AND gate operates with skyrmions. Skyrmions have also been used for other things. For example, here, skyrmion in this magnetic disk, under the effect of spin current, the skyrmion starts to turn. There is a reader here, therefore the size, the motion of the skyrmion is like that, and the output measured at the reader is an oscillating. So this is an oscillator using in the gigahertz region proposed for skyrmions. I would like to show this work done with my collaborator, Dr. Vio Cotrina. This is the possibility through simulation of creating skyrmions and skyrmioniums, starting with a single domain and applying oscillating fields. This is the skyrmion spectrum, showing the skyrmion spin wave modes, typically 3 large peaks. And the skyrmionium has also 3 large peaks here in the gigahertz region. And exciting the single domain with these frequencies, but not only these frequencies. One can generate skyrmions and skyrmioniums. This is illustrated here. This is the frequency mode 1, mode 2, and mode 3. This is the time, and this is a topological charge. And then we see that by applying the 3 modes, the different modes, one ends up with a topological charge of 1, which characterizes a skyrmion. This is the time dependence of the shape of the structure of the disk, as one in about 4 or 5 nanoseconds one creates the desired structure. This is again the creation of skyrmionium, the same idea, but using the modes corresponding to the skyrmionium. Another application that we have examined with the simulation was the possibility of switching skyrmioniums. Here is a skyrmionium. It has white center, which means white means magnetized upwards, and black means magnetized downwards. And we demonstrate here how applying the pulses of this frequency one can switch the skyrmionium. which is obviously a very interesting possibility for devices where one bit would be magnetization up and the other bit would be magnetization down. This is illustrated, also a video that we will not see here. The same idea was also appeared in the literature that recently, 2021, with a structure not on a disk, but skyrmions that appeared on a hemispherical shell of magnetic material. These are the corresponding modes, frequency modes, and the same thing applying the fields. One turns skyrmion and skyrmion and can modify them. Okay, so my conclusions are that skyrmions are topological protected vortex structure. Their formation is produced, favored by Chalogitsky-Maury interactions. They may be classified how the magnetic moments turn along a diameter, and the angle that the magnetization turns along a radius, pi to pi, 3 pi, and so on. They can be displaced with small current density, and they are associated with new observed effects, such as Skyrmion Hall effect and topological Hall effect. Applying oscillating magnetic fields, one can tailor the desired structure, starting from a magnetized disk. And there are also many applications already considered for skyrmions, such as racetrack memories, logic gates, nano-oscillator transistors, neuromórfic computing, and so on. These are for names of the collaborators, and I thank you for your attention. Thank you very much.
Oh, thank you very much, you, Professor Alberto Passos Guimarães. Very interesting talk, and I suppose we have a lot of questions for you. However, we will have only one question for each one here, and after that, we'll have questions from the audience, remote audience, of course. And so, more on time, thank you very much for your rich talk. I would like to invite now to question Professor Ángel Bustamante. Por favor, Ángel.
Obrigado, Isaías. Sí, yo tenía una pregunta respecto a la temperatura. Estos sistemas nano ordenados son muy, ¿cómo puedo decir? Son muy, dependen mucho de la temperatura. ¿Usted sabe qué rango de temperatura puede hacerse estos rangos de vórtices de los skyrmiones? ¿Está en orden de nanokelvin, milikelvin? No sé, ¿me podía hablar de eso?
No, ellos han sido observados a temperatura ambiente.
Ah, ok.
En laboratorio se puede verlos a la temperatura ambiente.
A temperatura ambiente, ok.
Y bueno, las simulaciones que he mostrado siguen arriba de la temperatura ambiente, algunas de ellas.
Oh, bueno. Obrigado.
Muchas gracias, Ángel. El próximo a hacer la pregunta es el profesor Albino. Albino, abra su cámara, por favor.
Pois não, professor?
Como é que eu faço aqui para eu ver, que eu não vejo vocês?
Não vê?
Eu só estou vendo minha apresentação. Ah. Cadê o Albino?
Pode me ver aqui? Eu estou no Skyrmion. Rede Skyrmion.
Albino, eu não vejo você. Aliás, eu não vejo você há mais de 10 anos.
Pois é, a gente tem andado por caminhos paralelos e diferentes. Bom, mas aí a gente vai se encontrar aí quando tiver a criação de um par Skyrmion anti-Skyrmion. Veja, meu amigo, sua palestra é muito interessante. aprendi muito, né? Gostaria de poder contribuir nessa área, mas a gente não pode fazer tudo na vida, né? Eu tenho aqui uma pergunta simples da minha ignorância no assunto. Tem muita coisa relacionada com vórtices e antivórtices em materiais supercondutores, né? E aí, a pergunta que eu acho que é aquela que a gente diz que não quer calar, é quando é que a gente vai poder usar Skyrmion para fazer computação quântica? Ou não é possível?
Aí você... Computação quântica é uma coisa complicada, né?
Não, é mais simples do que hoje.
Já existem aplicações, artigos tratando de aplicações neuromórficas, onde o Skyrmion ele é usado mais pelo fato de que há uma forma de gerá-los com propriedades aleatórias. Então, é uma forma de gerar números aleatórios, pelo que eu compreendi na literatura. Então, existem aplicações, cálculos neuromórficos, isso é um paralelo com os neurônios, como funcionam os neurônios. Mas sobre computação quântica, há referências, mas eu não saberia explicar para você. Agradeço a sua pergunta, de qualquer modo.
Tá bom, Alberto, muito obrigado. E vamos nos encontrar quando acabar essas desgraceiras aí causadas pela Covid.
Obrigado, Albino, pela pergunta, Alberto, pela resposta. E vamos agora convidar o professor Jairo Roras, da Universidade Nacional de Colômbia. Jairo, adelante. Jairo, se não está, eu passo a palavra para Davi. Davi?
Oi, tudo bem, Isaías? Eu acho que o Jairo teve que sair, que chegou o pessoal da internet em casa aqui a fazer uma atualização do sistema. Eu tenho uma pergunta talvez muito básica a respeito aos mecanismos dos Skyrmions magnéticos, que o professor falou da interação relativística de Jalosink e Morillard, e nessa interação eu tenho entendido que a dependência do tamanho dos Skyrmions são dos ordens de nanômetros e depende do campo externo. Então, isso também, a espessura da amostra tem alguma coisa a ver com isso, quando são filmes finos? Essa é a minha pergunta.
Davi, se puder, abra a sua câmera.
Eu estou no celular, eu vou tentar
sim,
aqui.
Sem problema.
Aqui eu estou... Dá para ver?
Sim,
professor, um prazer, professor. Muito obrigado pela palestra, muito interessante.
Obrigado. A dimensão, the dimension of the ribbons, the dimension of the systems is very relevant, of course, and the simulation has to look for the right thickness of the disc, in many cases, of the ribbons. So these are nanoscopic dimensions usually, and the cables have from say 10 nanometers to 1 micrometer size. This is the range, and then one looks in the simulation for the materials that provide these exchange, the values of the exchange, and the value of the DMI interaction, which arises either in the mode of the material when there's no center symmetry, and in the surface, there are contributions of the mind that arise from the surface. So to do this experimentally is complex work. They have done, many groups have done experimental observation of individual skyrmions moving, or experimental observation of networks of skyrmions organized, regularly organized as a lattice. So these are generic comments that I'm using to reply to your question.
Okay, thanks very much. Obrigado, Isaías. Obrigado.
Gracias. Gracias a tu pregunta, David. Y ahora vamos a llamar el representante de la Universidad de Barranca, el profesor Ricardo Celis.
¿Cómo está, Isaías? Muy buenos días. El doctor Guimarães, muy buenos días. Excelente su ponencia, muy didáctica y muy ilustrativa. Quería saber si es que estos vórtices se forman en materiales magnéticos y si es posible encontrarlos también o que se formen en otro tipo de materiales que no sean magnéticos, por ejemplo. Gracias, doctor.
No, es necesario que sean magnéticos, porque es una estructura de momentos magnéticos que tiene una estructura especial, o sea, es necesario de partida que sea un material magnético. Esto es necesario. Puede ser una película magnética sobre otro material no magnético, pero es el interior de la película que se va a pasar esos hechos de propiedades convencionales.
Excelente, muy amable. O sea, en un material condensado, por ejemplo, no podría ser posible que se formen los skyrmions.
No.
Muchas gracias, doctor. Muy amable.
Gracias a usted.
Muito obrigado, professor Ricardo. E agora, completando essa pergunta, Alberto, se você está numa parte magnética e tem uma junção que não é magnética e tem do outro lado um material magnético, consegue-se dar saltos de skyrmions, tipo são os saltos de Josephson, os supercondutores?
Não conheço.
Tá. Ok. Ahora nosotros vamos a llamar al profesor Arturo Martínez de Sinvestán de México. Arturo, es con usted.
Sí, buenos días. ¿Sí me escuchan?
Si pudieras abrir la cámara.
Sí, sí. A ver si ya me veo. Sí, acá estoy. Buenos días. Muchas gracias, doctor. Alberto, gracias por la presentación. Pues también gracias por la invitación a Luis, que es el que ya conozco, y a ustedes por la iniciativa que están haciendo para realizar estas ponencias. Gracias.
Arturo, nosotros no comprendemos, no ouvimos tu pregunta.
No tengo pregunta. No tengo pregunta.
Sí, claro, gracias.
Solo me estaba preguntando sobre mi participación, no, gracias.
Tá, muy bien. Alberto.
Sí,
okay.
Vê que há um mensaje de Ximena.
Sim, sim. Eu vou passar para ela daqui a pouco. Agora nós temos que ouvir a pergunta do professor Pedro Murica, mas eu penso que ele teria que sair. Agora sim, Ximena, pode falar?
Muchas gracias, muy buenos días. Muchísimas gracias por una conferencia tan excelente. El profesor Jairo Roa de la Universidad Nacional de Colombia, pues ahorita está presentando un poquito de problemas técnicos y me pidió el favor de repetir la siguiente pregunta. ¿Cómo el profesor ve que todos estos comportamientos de los Skyrmions y todos estos mecanismos podrían aplicarse en dispositivos para almacenamiento de información en medios magnéticos? Muchísimas gracias.
Bueno, yo he mencionado las racing track, memorias, son memorias que tienen una estructura y ya están, no sé, ya existen patentes con memorias de pared de dominio, pero con Skyrmions se puede utilizar la misma geometría y las mismas ideas que contenidas en el proyecto de IBM que empezó con la creación de la patente de memorias de corrida. Esa es la aplicación más evidente de los Skyrmions en lugar de la pared de dominio, pero en la misma geometría, en el mismo approach.
Gracias, Alberto. Agora, gostaria de saber se os representantes das universidades associadas têm perguntas de sua audiência. Sí, Santos, Ricardo, puede
Sí,
hacer.
sí, me preguntan aquí si es que el objetivo principal de los Skyrmions es almacenar mucha información y con poquísimo uso de energía. ¿Es posible una producción industrial? Muchas gracias.
Sí, yo creo que es digamos, una tecnología muy distinta de la tecnología de los microcircuitos. O sea, utilizar, ya existe, hace un mes salió la primera memoria en gran, y la memoria magnética, que hace muchos años lo de en los artículos, ahora ya es un componente que se puede poner, que se va a comprar en las computadoras. O sea, ya empiezan a existir memorias y asociadas a circuitos electrónicos que van a estar en las computadoras en los próximos años. Sobre los Skyrmions todavía no están ahí tan cerca de la producción, pero me imagino que van a llegar a sustituir otras memorias que existen actualmente.
Bom, gracias, Alberto.
Muchas gracias, doctor. Muy amable, gracias.
Gracias, Ricardo. Muy bien. Bueno, ahora nosotros gustaría que todos que pudiesen abrir las cámaras para saudarmos al profesor Alberto para la excelente charla, Albino, Luis, todos los otros. Ahora consigue ver Albino.
Gracias bien, Albino.
Albino está en la red de Skyrmions.
Eso.
Muy bien.
La red de Skyrmions estaba bien.
Está bien, Ricardo.
Ángel,
Bueno,
muito bom ver
vamos
você.
dar uma salva de palmas ao professor Alberto. Muchas gracias, profesor Alberto. Thank you very much. And
Una caipirinha virtual.
sim, claro. Muito bem.
Parabéns, Alberto, e muita saúde, meu amigo.
Obrigado, tudo de bom para vocês, hein? Saúde também para todos. Muito obrigado pela atenção.
Muito obrigado.
Relembrando as universidades participantes, que são as universidades: Universidade Federal Rural do Rio de Janeiro, Universidade Federal de Pernambuco, Brasil, Universidade Nacional Maior de São Marcos, a Universidade Nacional da Colômbia, Universidade de Barranca, no Peru, Simvestar, também no México. Muito obrigado a todos e agora só temos que preparar para o almoço.
Próxima palestra. Bom
Bom
dia a todos. Muito obrigado. Arrivederci.
Muchas gracias.
Chao a todos.
Hasta luego, Lucho. Nos vemos.
Tchau, tchau.
Mais uma vez, obrigado.
Oi, obrigado.